On July 14, 2015, a piano-sized spacecraft moving faster than any object humans have ever launched screamed past a small, icy world nearly 3 billion miles from the sun, captured everything it possibly could in a matter of hours, and then kept going, never to slow down, never to turn around, never to return. That spacecraft, NASA's New Horizons, remains the only mission in human history to have visited Pluto up close. And the fact that it took over 9 years just to get there and that nothing has gone back since tells you almost everything you need to know about just how brutally difficult it actually is to reach the edge of the known solar system. This isn't a story about something impossible. We've already done it. This is the real story of exactly how hard it was, why a single flyby was the absolute limit of what was achievable, and why actually orbiting or landing on Pluto remains one of the genuinely unsolved problems in modern spaceflight. To understand why reaching Pluto was such an extraordinary engineering challenge, you first have to understand just how little anyone actually knew about it before New Horizons arrived. Pluto was discovered in 1930 by the American astronomer Clyde Tombaugh, working from photographic plates taken at the Lowell Observatory in Arizona. For the better part of a century afterward, even the most powerful telescopes on Earth, and later the Hubble Space Telescope in orbit, could only resolve Pluto as a tiny, blurry smudge of pixels, enough to detect its existence, estimate its orbit, and eventually discover its largest moon, Charon, in 1978. But nowhere near enough detail to make out surface features, terrain, or anything resembling an actual map. That meant any mission attempting to reach Pluto would be navigating toward a target that mission planners had never actually seen with any real clarity. Every other planetary mission in NASA's history had at least some baseline of prior imagery to work from. Pluto offered almost none of that. Engineers were essentially designing a multi-billion-mile journey toward a destination they'd have to discover in real time, on the way there, using onboard instruments to refine their own understanding of exactly what they were approaching, mere months before arrival. This uncertainty extended even to some of the most basic facts about the Pluto system. Prior to the mission, scientists weren't entirely sure how many moons Pluto actually had. Charon had been known since 1978, but the Hubble Space Telescope discovered 2 additional small moons, Nix and Hydra, in 2005. The same year New Horizons was undergoing its final pre-launch preparations, and 2 more still, Kerberos and Styx, were discovered in 2011 and 2012, while the spacecraft was already years into its journey. Each new discovery required mission planners to reassess potential hazards along New Horizons' planned flight path, since an unexpected ring of debris or an undiscovered small moon directly in the spacecraft's path could have destroyed it during the flyby. A genuinely serious risk, given that a collision with even a small particle at New Horizons' extreme relative velocity could be catastrophic. Engineers spent the final approach phase of the mission searching intensely for any sign of additional rings or debris hazards, using the spacecraft's own cameras to scan the region ahead of its planned trajectory, ready to divert to a backup flight path if anything dangerous turned up. Fortunately, none did, and the primary flight path was confirmed safe only in the weeks immediately before the encounter itself. Pluto orbits the Sun at an average distance of roughly 7 billion miles, though that distance varies considerably because Pluto's orbit is unusually elongated compared to the planets. At its closest approach to the Sun, Pluto can come within about 8 billion miles. At its farthest, it swings out to nearly 6 billion miles. New Horizons launched on January 19, 2006, when Pluto happened to be a little over 3 billion miles away, and even traveling faster than any spacecraft ever launched before it, the journey still took more than 9.5 years. To put that distance in perspective, light itself, the fastest thing in the universe, takes more than 4 hours to travel from the Sun to Pluto at that typical distance. New Horizons, despite launching at roughly 36,000 miles per hour relative to Earth, fast enough to reach the Moon in about 9 hours, a trip that took the Apollo missions 3 days, still needed nearly a decade to cross that same span of space. A reminder of just how genuinely vast the outer solar system is, even to a spacecraft moving faster than anything else humans have ever built. Launching a spacecraft at that speed required its own set of extraordinary engineering decisions. New Horizons was launched aboard an Atlas V rocket configured with additional solid rocket boosters and an extra upper stage specifically added to maximize the spacecraft's departure velocity, a configuration more powerful than what's typically used for missions closer to home. Even loading the spacecraft with fuel required unusual precautions. New Horizons carried a small amount of plutonium-238 to power its radioisotope thermoelectric generator, the same basic technology used aboard the Voyager spacecraft decades earlier, and safety officials required a formal risk assessment process before launch, given the small but non-zero possibility of a launch failure that could disperse radioactive material. That review process contributed to a brief additional delay before the mission's final launch date was confirmed, adding one more layer of complexity to a mission that already had almost no room for schedule slippage, since Pluto's own orbital position relative to Jupiter meant only a narrow multi-week launch window in January 2006 would allow the spacecraft to use Jupiter's gravity assist at all. Missing that specific window would have meant either abandoning the Jupiter flyby option entirely, adding years to the total travel time, or delaying the entire mission by more than a decade to wait for another favorable alignment. Even at that record-setting launch velocity, New Horizons engineers needed an additional boost to make the mission's timeline work, and they got it by borrowing momentum from Jupiter itself. In February 2007, roughly 13 months after launch, New Horizons passed within about 4 million miles of Jupiter, using the giant planet's enormous gravity to perform what's known as a gravity assist, a maneuver where a spacecraft essentially steals a small amount of a planet's own orbital momentum, gaining speed and bending its trajectory in the process, all without expending any of its own limited fuel supply. That single flyby added roughly 9,000 miles per hour to New Horizons' velocity relative to the Sun, shaving about 3 years off the total travel time to Pluto. Without it, the mission would have taken well over a decade just to reach its primary target, stretching an already difficult mission even further and adding additional years, during which any single onboard failure could have ended the entire effort before it ever reached Pluto at all. The Jupiter flyby wasn't purely a speed boost either. Mission scientists used the opportunity to test and calibrate New Horizons' scientific instruments on a real target, capturing detailed images of Jupiter's atmosphere, its faint ring system, and its 4 largest moons, effectively turning what could have been a purely mechanical gravity assist maneuver into a genuine bonus science campaign, gathering data on the Jupiter system years before the spacecraft's primary mission at Pluto had even truly begun. Here's the detail that explains, more than any other single fact, exactly why reaching Pluto in the way New Horizons did represented the practical limit of what current spacecraft technology can accomplish. New Horizons was never going to orbit Pluto. It was only ever designed to fly past it at extremely high speed, gathering as much data as possible during a brief window of closest approach, before continuing onward into deep space permanently, with no ability to turn back. The reason comes down to a basic and unavoidable problem in orbital mechanics. To place a spacecraft into orbit around any planetary body, rather than simply flying past it, the spacecraft has to slow down dramatically once it arrives, canceling out enough of its own velocity that the target body's gravity can actually capture it into a stable orbit rather than letting it continue past. Slowing down that much requires firing engines in the opposite direction of travel, a maneuver that consumes an enormous amount of fuel. And the faster a spacecraft is traveling when it arrives, the more fuel that braking maneuver requires. New Horizons was deliberately built to travel to Pluto as quickly as possible, specifically because taking a slower approach would have added years, possibly over a decade, to an already extraordinarily long journey. But that same design choice, optimized for speed, made an orbital insertion at Pluto essentially impossible using any fuel supply the spacecraft could realistically have carried that far from the Sun. Carrying enough propellant to both reach Pluto quickly and then slow down enough to orbit it once it arrived would have required a vastly larger and heavier spacecraft than what could realistically be launched and accelerated using any rocket available at the time, and even then, the total mission cost and complexity would have ballooned dramatically. Mission planners made a deliberate trade-off, sacrificed the ability to orbit Pluto entirely, in exchange for a mission that could actually be built, launched, and completed within a human researcher's working career, rather than stretching across multiple decades. That decision meant New Horizons' entire encounter with Pluto had to be executed in a single high-speed pass with essentially zero room for error. The spacecraft flew past Pluto at a relative speed of roughly 3,800 miles per hour, meaning its closest approach, the single moment when it gathered the overwhelming majority of its most valuable scientific data, lasted only a matter of hours before Pluto was already shrinking behind it, too distant for any further detailed observation. There was no opportunity to circle back for a second look at something that caught scientists' attention, no chance to adjust the camera angle after the fact if an image came back slightly off target, and no ability to react in real time to anything unexpected discovered during the flyby itself because of the enormous communication delay involved. At Pluto's distance, a radio signal from New Horizons took between 4.5 and 5.5 hours to reach Earth, depending on the exact positions of Pluto and Earth at the time, and any command sent back took just as long to arrive. That meant mission controllers on Earth couldn't watch the encounter unfold and make adjustments as it happened. By the time any signal reached Earth confirming what the spacecraft was seeing, the actual flyby was already hours in the past, and by the time any new instruction could be sent back in response, the entire encounter would already be over. Every single second of New Horizons' brief window near Pluto had to be planned in advance, programmed into the spacecraft's onboard computer months before arrival, and executed entirely autonomously, without any real-time human oversight or correction. Engineers spent years designing and testing that precise sequence of instructions, simulating the exact timing of every camera exposure, every instrument activation, and every slight adjustment in the spacecraft's orientation, because there would be no opportunity to fix a mistake once the actual flyby began. That preparation involved an almost obsessive level of rehearsal. Mission scientists and engineers ran the entire encounter sequence through simulations dozens of times in the years and months leading up to the actual flyby, testing how the spacecraft's onboard computer would respond to a wide range of possible scenarios, including potential hardware glitches, unexpected changes in spacecraft orientation, or timing errors of even a fraction of a second, since any such error could mean an instrument pointed slightly the wrong direction at exactly the moment it needed to capture its single, irreplaceable image of a particular surface feature. Just 10 days before the actual encounter, on July 4th, 2015, the spacecraft experienced an unexpected computer anomaly that temporarily put it into a protective safe mode, causing a brief loss of communication and raising serious concern among mission engineers that the flyby itself, just over a week away, might be jeopardized. Engineers on the ground worked urgently to diagnose the problem, eventually tracing it to a timing conflict in the spacecraft's command sequence, and successfully restored full functionality with just enough time to spare before the critical encounter sequence needed to begin. Had that anomaly occurred even a few days later, or taken longer to resolve, there might not have been enough time left to recover before the flyby's precisely timed sequence was set to begin, potentially costing the mission its only opportunity to gather close-up data after 9.5 years of travel. That near miss illustrates just how little margin for error this kind of mission actually allows. Unlike a mission orbiting a planet, where a spacecraft gets repeated opportunities across multiple orbits to recover from a problem and try again, New Horizons had exactly one pass, at exactly one moment, and any sufficiently serious malfunction in the days immediately before that moment could have ended the mission's primary scientific objective entirely, regardless of how successfully the preceding 9.5 years of travel had gone. Even after the flyby itself was successfully completed, the mission wasn't finished, because getting all the collected data back to Earth turned out to be its own extraordinary technical challenge. New Horizons' onboard data storage held far more information than the spacecraft's limited communication system could transmit quickly across the vast distance separating it from Earth. Its low-power transmitter, running on a radioisotope generator similar to the ones powering the Voyager spacecraft, could only send data back at a comparatively slow rate, given the sheer distance the signal had to travel, and given how faint that signal had already become by the time it reached Earth's receiving antennas. As a result, it took New Horizons approximately 16 months, stretching from shortly after the July 2015 flyby all the way into October 2016, to fully transmit every piece of collected data back to Earth. Mission scientists made deliberate choices about which images and measurements to prioritize sending back first, ensuring the most scientifically valuable data arrived early, while less urgent material was gradually downloaded over the following year as bandwidth allowed. That extended downlink period meant some of the most detailed insights from the Pluto encounter didn't reach scientists until well over a year after the actual flyby had already taken place, a genuinely unusual delay compared to missions closer to home, where data can typically be transmitted back to Earth within hours or days rather than months. Despite all of those constraints, the single brief flyby produced discoveries significant enough to fundamentally reshape scientific understanding of Pluto. Before New Horizons arrived, Pluto was widely assumed to be a geologically inactive, ancient, heavily cratered world, similar in character to many other small, icy bodies in the outer solar system. Instead, New Horizons images revealed vast, smooth plains of nitrogen ice, informally named Sputnik Planitia, showing almost no impact craters at all, a strong indication that the surface has been geologically active and resurfaced relatively recently, rather than remaining frozen and unchanged since the solar system's earliest history. The spacecraft also revealed towering mountain ranges made of water ice, rising several miles high in places, alongside evidence of an underlying layer of liquid water, potentially existing beneath Pluto's icy crust. It captured detailed images of Pluto's largest moon, Charon, revealing a surprisingly complex and varied surface of its own, including a mysterious dark reddish region near its north pole that scientists believe may be caused by gases escaping from Pluto's own atmosphere, drifting across space and settling onto Charon's frozen surface. New Horizons also discovered a surprisingly extended layered atmospheric haze surrounding Pluto itself, extending far higher above the surface than scientists had previously modeled. The presence of that vast nitrogen ice plain, Sputnik Planitia, turned out to carry an unexpected significance well beyond its striking, smooth appearance. Follow-up analysis of New Horizons gravity data suggested the plane sits within a large impact basin, and its position on Pluto's surface, roughly opposite Charon in orbital terms, may be linked to a subtle but real gravitational interaction between Pluto and its unusually large moon. Some researchers have proposed that a concentration of dense material beneath that basin, potentially including a layer of liquid water, could be helping to keep the nitrogen ice plane-oriented in its current position relative to Charon over long timescales, a genuinely intricate piece of orbital and geological physics that nobody could have anticipated before the flyby actually provided detailed enough data to notice the pattern in the first place. New Horizons also captured the first close-up look at Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra, revealing them to be small, irregularly shaped bodies, some tumbling chaotically rather than rotating in an orderly, predictable way, likely a consequence of the complex gravitational environment created by Pluto and Charon's close mutual orbit. Pluto and Charon are sometimes described as forming a binary system rather than a simple planet-moon pairing, because Charon is large enough, relative to Pluto, that the two bodies actually orbit a shared center of mass located outside of Pluto's own surface, a genuinely unusual arrangement not replicated anywhere else among the planets and their moons in our solar system. None of these discoveries would have been possible without physically sending a spacecraft that close, because the distance involved makes even the most powerful telescopes available from Earth, including space-based observatories, incapable of resolving this level of surface detail. Prior to the flyby, the best available images of Pluto, captured by the Hubble Space Telescope, showed only a handful of extremely blurry light and dark patches, nowhere near enough detail to identify mountain ranges, smooth ice plains, or atmospheric layers. New Horizons' mission didn't end at Pluto. After the 2015 flyby, mission planners used the spacecraft's remaining fuel to adjust its trajectory slightly, redirecting it toward a second, much smaller target deep within the Kuiper Belt, the vast region of icy bodies beyond Neptune's orbit where Pluto itself resides. On January 1st, 2019, New Horizons flew past a small, distant object officially named Arrokoth, becoming the most distant object ever explored up close by a spacecraft from Earth, at a staggering distance of roughly 1 billion miles from the Sun. That second encounter arguably pushed the mission's engineering challenges even further than the original Pluto flyby had. Arrokoth is a small, irregularly shaped body, discovered specifically because scientists searched for a suitable secondary target using the Hubble Space Telescope after New Horizons had already launched, since no previously known Kuiper Belt object happened to lie conveniently along the spacecraft's existing trajectory. Targeting an object that small, that distant, and that recently discovered, using a spacecraft that had already been traveling through space for over a decade, represented an even more demanding navigational challenge than the original Pluto encounter, requiring extraordinarily precise trajectory corrections based on extremely limited advanced knowledge of exactly where the target object would actually be at the moment of closest approach. Arrokoth itself turned out to be scientifically remarkable in its own right. New Horizons images revealed it to be a contact binary, two separate lobes of material that gently merged together at extremely low velocity sometime in the early history of the solar system, rather than colliding violently the way many other planetary building blocks are believed to have formed. Because Arrokoth orbits so far from the Sun, in one of the coldest, most undisturbed regions of the solar system, scientists believe it has remained essentially unchanged since its formation over 4.5 billion years ago, making it one of the most pristine, unaltered building blocks of the early solar system ever directly examined by a spacecraft. That level of preservation simply isn't available anywhere closer to the Sun, where billions of years of solar heating, collisions, and other disruptive processes have reshaped nearly everything else humanity has ever studied up close. Reaching Arrokoth required New Horizons to use its remaining fuel with extraordinary precision, since the spacecraft had no ability to refuel and needed to preserve enough propellant not just for the necessary trajectory adjustments toward its new target, but for ongoing minor course corrections and attitude control for the remainder of its extended mission. Mission engineers calculated that even small errors in the initial post-Pluto trajectory changes could compound over the roughly 3.5 years of additional travel time to Arrokoth, potentially causing the spacecraft to miss its second target entirely after having already achieved its historic primary objective at Pluto. More than a decade after the historic flyby, no spacecraft has been sent back to Pluto, and none is currently funded or in active development to do so. The reasons come down to exactly the same fundamental challenges that made the original mission so difficult in the first place, only now applied to an even more ambitious goal, actually orbiting or landing on Pluto, rather than simply flying past it at high speed. Orbiting Pluto would require a spacecraft capable of carrying vastly more fuel than New Horizons did, specifically to perform the kind of dramatic braking maneuver needed to slow down enough for Pluto's weak gravity to capture it into orbit, rather than continuing on past it into deep space. Landing would be harder still, requiring not just orbital insertion, but a controlled, powered descent onto an icy, poorly understood surface, using a communication system that would still face the same multi-hour delay, separating any command sent from Earth and its actual execution millions of miles away. Every one of these challenges that made the original New Horizons mission so difficult would apply just as strongly, if not more so, to any future mission attempting something more ambitious than a single flyby. Beyond the pure engineering challenges, there's also a practical resource question that any future Pluto mission would have to contend with. New Horizons relied on a supply of plutonium-238 to power its radioisotope thermoelectric generator, the same kind of power source used aboard the Voyager spacecraft and other deep space missions traveling too far from the Sun for solar panels to provide adequate power. That specific isotope is produced through a slow, deliberate nuclear process, and global production capacity has historically been limited, meaning any new mission requiring a similar power source has to compete for a genuinely scarce resource, planned years in advance, alongside other proposed missions with their own power requirements. That scarcity alone has been enough to meaningfully constrain how many outer solar system missions can realistically be developed at any given time, regardless of how scientifically compelling a proposed follow-up mission to Pluto might be. Some mission concepts for a Pluto orbiter have been proposed and studied by scientists in recent years, exploring more advanced propulsion technologies that could potentially make orbital insertion more feasible than it was for New Horizons. But none of these proposals has yet received the kind of sustained funding and formal mission approval needed to move from a scientific concept into an actual developed spacecraft, meaning, for now, New Horizons' single flyby remains the entirety of humanity's direct, close-up knowledge of Pluto, gathered during a window of just a few hours, after a journey of nearly a decade. There's no need to frame any of this as evidence that Pluto is somehow unreachable, because the real story is already remarkable enough without that exaggeration. Reaching Pluto required building the fastest spacecraft ever launched from Earth, borrowing speed from Jupiter's own gravity, executing a single irreversible high-speed flyby planned down to the second years in advance, waiting over 16 months just to receive all the data back afterward, and doing all of it based on almost no prior knowledge of what the spacecraft would actually find once it arrived. That's not impossible. It's simply one of the most difficult, most carefully engineered achievements in the history of spaceflight, accomplished exactly once, by a single spacecraft, using nearly every trick available in modern orbital mechanics, communication engineering, and autonomous spacecraft design, and not yet repeated because doing it again, and doing it well enough to actually orbit or land, remains a challenge nobody has yet solved. If this changed the way you think about what it actually took to reach the edge of the solar system, subscribe for more real, well-sourced breakdowns of the missions that pushed spacecraft engineering to its absolute limits, because somewhere out past Pluto right now, still traveling outward at roughly 33,000 miles per hour, New Horizons continues its own one-way journey into the Kuiper Belt, carrying with it the only close-up data humanity has ever gathered on a world 9.5 years and 3 billion miles away.